everyone. Nice to see you. I hope you weren't discouraged by quantum physics in the title. I will try to make it level, introductory level. So please interrupt me at any moment. I thought there was already hands, and I was feeling excited. So fast. Yes. So basically, I want to tell you a bit about challenges of modern quantum physics that can be addressed actually with machine learning, and I will show you two examples, two snippets of my work where I'm trying to develop new interpretability tools for machine learning applied to quantum physics and solve some practical challenges there. So this is the this is the outline. So the first part will be interesting. Okay, will be exactly discussing this challenges of quantum physics. And given that I know there is a language barrier, I will try to break it into small parts, and then it will also be a crash course of quantum physics. So after this part, you will know or you will remind yourself what's quantum superposition, what's wave function, and all that. And then I will tell you about two research projects I was doing. One is using graph algorithm for finding new experimental setups for quantum sciences, and the other where we're developing new interpretable network to do something cool with phases of matter. Okay, and then I will show you, let's say, open avenues. So first things first. Okay, so the main challenge, the largest challenge that quantum physics is battling with since the beginning of its birth, is the fact that we would like to understand the behavior of many interacting particles in a quantum world, and finding and understanding their behaviors is actually very, very difficult from the theoretical and computational point of view. But let's make it maybe more concrete. So basically, this challenge is the quantum many-body problem, and the problem is let's assume some setup. You define some interactions between your particles. Maybe you want to put some electric field on top of that. You define everything that is happening in your setup, and then you want to understand what's the resulting behavior of your system. Because unfortunately, only knowing elements of your system does not allow you immediately to understand what's the behavior of the system, because there may be some emergent properties, and there may be competition between different terms, different elements of your system. So basically, this is the main problem of quantum physics. So you define a set of conditions that we dubbed Hamiltonian, which is whatever, this H with the hat. And we want to, from this, infer the behavior of the system, and we describe the behavior of the system as we dub it wave function. So basically, from Hamiltonian, we want to know the wave function. Good thing is that we at least know how to even approach this problem, which is you can try out many behaviors, many wave functions, and the one that has a minimal energy will be the one that your system will take. So basically, you can guess your wave function, guess, or optimize it, and the one that has minimal the energy that minimizes this part, this is your solution.
Is that because some sort of in equilibrium at that point or something?
You can think of it as, your system wants to have the smallest energy. It's a tail all that time, and it's also in classical physics and all that. So basically, you want to reach this equilibrium, let's say, right? So you have fractions, and you're looking for a situation or like configuration that doesn't create any tension. So that's the intuition exactly. Okay, So, but this means already like, okay, so we can iterate over various behaviorist wave functions and just find the energy. Why it's not a valuable approach? It's because of the exponential complexity of the problem. So imagine, let's start with the simplest yet very interesting object that physicists study, which is spin 1/2. You can just think of it as an arrow that has two possible states, up and down. Also, like you can think of it also as a okay, no, I want word. So very simple discrete object. And now let's do a very basic math. With one spin 1/2, you have two possible states. This means that you can check up this state up, state down, calculate the energy, and your system will choose the one of the smaller energies. Right. With 2, it's 4, and it's still fine. And with n, it's 2 to the n, and it's getting much more. It basically gets more and more expensive to go over every possibility, but it's still even worse than that. This is actually classical setup because there was nothing quantum so far. This is just, but we already have 2 to the n, let's say, configurations we need to check. But in quantum world, it's even worse because we additionally have super, meaning our wave function will be a combination of all possible configurations. So it means that for one spin, there will be some chance that your system is in the up configuration and some chance that it's in the down configuration. So to optimize this part, it's not anymore just checking the two states. You need to find optimal A and B that will minimize your energy. So it's already getting, and they are also complex. These numbers are complex, so it's actually 4 numbers. With 2 spins, suddenly it's 4 numbers for 4 configurations, and you end up basically with a matrix 2n by 2n of complex numbers that you need to optimize to find the state with minimal energy that would solve your problem. And if you want to do it exactly, you can. It's called exact diagonalization. And we can do it on supercomputers for like n equal 30. But that's not enough to show all. Actually, I was absolutely too optimistic. No, maybe 30 is doable, but it's very, very, very hard already.
But so the matrix comes from the Hamiltonian?
Yes.
Okay.
Yes, exactly.
Because otherwise it's just a 2 to the n dimensional vector.
2 to the n, sorry?
Dimensional vector.
Yes. So yes. So it would be, you know how each configuration would contribute to energy via Hamiltonian. So each configuration and will create some elements of the matrix. And then if there are cross terms, they also will be non-zero. So it's not a diagonal in the matrix. It's basically, it can be sparse, but it's a regular matrix, unfortunately. And it okay. So we now know what quantum many-body problem is. Awesome. People even nodded. So we know how to find this behavior, this wave function, but finding is really hard.
But, sorry, assuming I can write everything down.
Yes.
And instead of 2 to the n, I say the 2 to the n, I call it capital N. Is it like a linear algebra problem?
Yes.
Okay, it's like finding an eigenvalue or something?
Yes, exactly. Yeah. So one of the 2 main formulations of quantum mechanics is matrices in our algebra. Okay, awesome. So that's the first challenge of quantum physics, going to larger sizes and more complex interactions that will create many more cross terms in this matrix that you want to diagonalize or solve in some other way. What's the second challenge? Okay, so if we just said that theory is very hard for quantum many problems, and computations can help up to some point. What about instead of trying to compute this, why not just build this quantum setup and observe? So that's the realm of quantum simulations or quantum. I dubbed it quantum experiments. It's quantum simulations, And this is a playground for quantum physics. It's basically, before we said we just choose some Hamiltonian, choose some set of all these interactions, fields, and properties of the system. Now let's build it, and then we just observe the resulting behavior. And that's how we can also gain insight in what's going on. So this would be also, okay, we solved it, but unfortunately it's again messy, because when we observe the quantum system, we need to measure it. And measurement is kind of messy in quantum world. So now very quick information about measurement. I don't know if you've heard, there's something like quantum collapse of the wave function. It means that if we started with 2 spins, and we don't know what exactly is this combination of all the possible configurations, but the moment when we observe it, it stops being this form. It collapses to one of the configurations that we actually observe. And that's what does it mean? It means that we need to make this measurement many times to get the statistics and understand what were the coefficients of the wave function. So it means that you never have, if you want to focus on machine learning or whatever, you never have access to wave function. You just have access to measurements done on this wave. So that's one challenge and trouble. And the other is at this level. So I just said, let's build a Hamiltonian, but it's not that simple. There are errors on the various levels. They are technical. There are technical problems, technical challenges. And actually, this is the reason why quantum computers are not there yet. So like control over all these elements in quantum experiments is super challenging. Okay, so basically those two are the second, let's say, largest challenge of modern quantum physics. So making this experiments in a verifiable way and without errors, and understanding what's going on. Okay, and the final thing is detecting and designing novel phases of matter. What are those? So now, basically, quantum phases are, I told you before that wave function is like a behavior, right? So quantum phases are classes of wave functions, classes of behaviors, let's say. So for example, and we use this language to kind of see, not to analyze system in every, let's say, every single slight variation of the Hamiltonian, but to make larger statements. So like, for example, this system can be superconducting. This system can be ferromagnetic. So we want to make more like general statements. So this is what phases of matter are. And the challenge is we have this experimental measurements of the quantum system. I already showed you that there's this problem of this non-deterministic collapse of the wave function. So we have just classical measurements that give you some information about full wave function, but it's not one-to-one relationship. And from that, we want to see what kind of interesting behaviors this system actually have, and exactly see these various wave functions that you have in the system. That's interesting because this is like the first step to do, for example, some interesting quantum materials that are exactly in some phase that can give you some benefit. So to see these different behaviors, the different phases of matter, physicists usually need to have a guess of what this phase is, and then they study the data to see whether they exhibit this behavior. But what about an unexpected behavior? How to look for phases we never expected to be in the data? That's an additional challenge.
Can you give some intuition as to these phases of matter? I mean, in the sense, like if I was trying to study matter,
yes,
I wouldn't put it into or emergent phases of matter or something. I would have trouble seeing it within a normal. Is it a simulation? Are we simulating something? Or are we really? This
can be either from theory, or this can be from experiments. So either measurements from your real system, or from the things you simulated on your computer. But I think that wasn't your question. So like,
I guess I'm confused what it means. Like, a wave function to be in a ferromagnetic or whatever state.
Yes. Maybe I should have started. So I'm not using precise terminology in this talk, okay. So basically, to be in a phase, it means that different wave functions have some common characteristics. For example, one very simple phase would be all spins are pointing up. And the other phase would be it's fully random. So the common characteristics of all these random things is that there is no pattern. And for example, in the second phase would be they're all up or all down. So there is this kind of common characteristic. There is more. And actually, I will be talking about that, but this understanding of this different behavior, this thing or this thing or this thing, it's called order parameters. There will be different order parameter in one phase and different order parameter in another phase. Was it helpful? Okay. Okay. So these were all, I would say, main modern challenges of quantum physics. And I would say since 2016, so not so long ago, there is a new data-driven paradigm. Usually I need to convince the audience more that this paradigm is used, but here I don't need to, which is basically instead of trying to use heuristics and our understanding of the system, how about let's just take all this generated data from this quantum simulation, from this quantum experiments, or from our computer simulations, and let's learn something from them. So basically, this learning from data is surprisingly new thing, I think, compared to all other domains in sciences. So and crucially, crucially, machine learning can help in solving every of this problem that I discussed before, and starting from exactly this quantum many-body problem, right? So I told you that it's difficult for us to guess this A and B, or even to represent this wave function in some Hamiltonian. So there's this quantum many-body problem, and people figure out that you actually can take neural networks that will try to map every possible configuration to this A or B, so this coefficients. And the key thing here is that we are kind of avoiding the exponential explosion, because it's one object that maps every possibility. So you don't need to store all to the end things. Hopefully the network can compress this knowledge. So it's called neural quantum states. Second challenge, I told you there was this problem of control and problem of and working on just measurements from experimental setups. And there are many ways that machine learning can help there. One thing is, I told you that you decide that, okay, these are the interactions we want to create in the experiment, this is the field, but that's not exactly what they end up doing. And they don't know errors on every of these terms. So what machine learning can learn the Hamiltonian from the data, and just to make sure it's like, yes, guys, you're doing the right thing, or no, guys, you're not doing the right thing. And usually it's the second. ML can also inspire new experiments, and I will show an example of that in this snippet. And there are many very practical, very classical challenges in like tuning the laser so it's perfectly aligned or stuff like this. So lots of room for improvement. Okay, and then in this phases of matter thing, which is exactly detecting unknown or surprising phases from the data, this is actually the first thing that people jumped into, because that's just basically pattern recognition, and people took all like image analysis tool and put it on the measurements, and it worked very, very, very well. But there are still some challenges to overcome, which is my second part of the talk, because we can tell that there are phases, but we don't know what differs them, what distinguishes this phase. Okay, so the roadblocks in the same exactly setup of problems. So I think those roadblocks are very general, but I think for science they are particularly problematic. Because without interpretability, and if you don't know and cannot really understand what your network learned in the problem, you didn't really gain any scientific knowledge from the solution that you gave. And scientists are usually unhappy with just a solution unless they don't understand how basically what it tells you about the world. And of course, there's problem of reliability. So as we all know, no uncertainty estimates, no guarantees, fragility against some perturbations, variety of problems that translate into specific roadblocks in quantum physics. So I told you about these neural quantum states that are used as a representation of a wave function as a way to solve the quantum many-body problem. So their optimization is super hard. And it's a very different class of problems than optimization of classical neural networks. And you please just trust me on that, because this would be another lecture on how neural quantum states work. But it's definitely the classical ML. So we don't understand why optimization is hard on local minima that we get stuck all the time, and landscape terrible. So solving this would be a major thing for quantum many-body problem. And then we also don't know if we're using different architectures of a network for these wave functions. Does it really change anything? What kind of different knowledge they encode? And so basically that, should we just use, I don't know, RBM or fully connected networks always, or maybe you should go for a transformer, and what does it change in this from the quantum perspective? In the experimental setups, obviously, like, reliability is an issue with, maybe your network will tell you that this is actually how you displaced your lasers, and you should correct for that, but it doesn't have to be correct, and you will trust this solution and just end up in an even worse place. And for the phases of matter, I already spoiled it a bit, which is we can detect the different phases and different behaviors, but we don't know why they are different, because the solutions are not independent. An additional very interesting, I think, problem for maybe more from ML community side is there are some phases of matter, particular, they're called topological phases of matter, maybe some of you heard, and neural networks struggle a lot in detecting them. So basically, we know that they are there, we can compute them, so there are topological phases of matter, and the network looks at the data and completely fails. So I think this also shows how scientific data sets sometimes create difficult challenges for neural networks, and can study when they fail. Okay, so we have these two phases of machine learning for quantum physics, and basically my job is to use all the promises while mitigating the roadblocks, and this was a crash course on quantum physics as well. So any questions on that? Because now we will delve into research.
Actually, remembering, like, when you do the measurements, you can get the amplitude, but not phases, or can you?
Yes.
Yeah. Or can you also?
So the answer will be a bit technical. So usually you can do measurements in different ways, not in different bases. And if you only do in one basis,
then you only get.
Then yes, but then you can do. But actually, recovering the phase can be also interesting. Maybe like active learning problem, where it tells you in which basis you should come to measurement.
So because I know nothing about like any experimental physics, like what does the changing the basis mean from, like, I don't know, like move the lasers, like what?
That's a very good question. I'm also not sure if, hold on, probably I can. I think you need to change, like physically the laser will be in the same spot, but it also has like frequency and the phase. And then I think you need to change the way that the light rotates in the laser. So, and then, but it's again something tunable. However, I would say I'm like 80% sure that that's the case. So, any more questions?
One question about the previous slide, the fact that the faces cannot be detected easily. Is it a problem of a database? Like there is a lack of enough representations for the.
No, that's actually a really cool problem. No, like you can give it all the data in the world and it won't see that for example, in some unsupervised way, it won't, if you tell this is phase 8 and if you do supervised learning, you will, I mean, it will memorize, but it won't really learn. If it's unsupervised, it won't notice. And it's what I'm saying is architecture dependent. So you can find solutions that will notice phases of matter, but with simple CNNs and with fully connected, you don't really. And the intuition that I have, I think, is when I was telling you about this 2 different phases of matter, so like spins going like this or all ordered, to know that these systems are different, you just need to look at the piece of the image. So so basically those are like local order parameters that you need to worry about. And with topological, if you look at all the spins, you don't see any order, and then you need to take some integral over something, but basically you need to look at the whole image at the same time. And I think maybe this speaks about neural network being focused on local features.
Can you also give us an example that what kind of materials do you work on? And for example, one of the examples of what kind of simulations do you do to get the data?
Okay, that's awesome question, because I just told you that this is very difficult to do on the computer and those are noisy. So yes, our data are definitely, it's definitely an issue. And when it comes to what models I'm doing maybe you will see in the snippets, but because our field is very in the early phases, like ML4, we are actually almost always start with solutions that are achievable computationally. So we do either exact diagonalization or tools that we know work very well, like tensor networks, to generate the data. And with experiments, so far there was experimental data are used only to detect different phases. And there, the noise usually doesn't matter that much. Or maybe it will create another phase that you then want to understand. So we have either access to messy experiments or to simulated data that are kind of small with insights. So the N is like doable.
So the simulations, for example, we test the functional theory. Do you use this?
I don't, but people are trying to merge the two approaches, because doing the DFT are very fine with black boxes, so ML works there.
Because you can get a wave function, right? But this is so.
But you also know that, like, if you are purist, you would say that the DFT wave function is not that like it's an approximation, and you're losing some information. But yeah, of course, you can also use things like quantum chemistry. I think it will depend on the problem you want to do. So if you want to do some exact measurements and understand exactly what's the Hamiltonian of your system, using approximated wave functions makes your job more difficult.
So the simulations you do is not like more than 3-4 electrons or something, right?
I would say, no, it's usually like up to, I don't know, 20, 30, yeah. But we don't even talk about that. I'm in the spin world, which is even easier. And if you go to materials and you really want to do electrons, then you do quantum chemistry, and there is little ML done there because people are very afraid of data quality.
I have very little knowledge about quantum physics, but as I remember from college, I think that quantum states are not stable, and the moment you find about a quantum state, it changes. So then how will it be done in simulation? Because the moment you find a state, or for a material, the state of that quantum world, you can go, so it will change. So then how can you find out what you found is the real state?
That's an awesome question. I told you that you need to do multiple measurements on the state to see the statistics, right? So what people do is you prepare the state in an experiment, you measure it, it destroys all your information, so you discard and make another whole experiment, and then do the single measurement and then discard. So you basically try to come back to the situation before the measurement by doing completely a new run of an experiment. So that's an experiment. And in simulation, this stops being true because as long as your wave function is not too large and you store it on your classical computer, it's like now there's no quantum collapse when you're observing. You just look at the numbers and it's fine. You're allowed to do that. So simulations are not prone to that. But the moment when you do it to experiment or to quantum computer, then definitely it's a difference. That's how you kind of try to avoid that.
When you're doing the experiment, I guess you're like evolving the state according to the Hamiltonian.
Yeah.
And like at some point it reaches the low energy state, but do you know when? Because like if you measure at some like intermediate states, like then you probably get something very different than.
So what people usually do, they start with something that is very easy to prepare, almost classical. So usually people start with, for example, all spins up, and then they just put super strong magnetic field that forgets all the quantum effects and just orients all them there, and then they do the quantum experiment. So with this first stage that you're talking about.
No, I mean like, how do you know that?
Oh, then you just do measurements across your time, and then you just analyze the data and your measurements and see what's going on. So it's not like you're waiting some special time t and then make a measurement. No, we just make a measurement, cancel, make a measurement, cancel, and then do it for every time step that you're able to.
I think so. My question is that it takes time to get to the ground state. You don't immediately get to the ground state.
Oh yeah, so usually, but don't necessarily. So okay, I understand what you're saying. So actually, experiments sometimes they're interested in one ground state, but we are at the level where we're interested in anything. So people just do this kind of dynamics of the system where you're not in the ground state, and they're also excited about that because then they learn about dynamics. But then you can also just
so they're sort of like measuring the system at some point in time where it hasn't actually necessarily converged,
yes.
and
that's
they're
fine.
happy with that.
Yes.
Okay.
Yes.
But I think there was some misunderstanding about the Hamiltonian. So the minimum energy kind of for the system, including time. I mean, it's always the minimum energy.
The ground state, yes, but we don't have to ground state it experiment.
More complex.
No, but I think isn't it like if my linear algebra recollection is correct, it's like you start from some state and then you multiply it by like e to the minus time times the Hamiltonian, thing like this.
Yes.
And you evolve time.
Yes.
If you do that for long enough, you get to like the minimum eigenvector. But in the in-between, you're like in some weirdo combination of eigenstates.
Yeah. Okay, then let's move to some project. So the first thing that I'm gonna tell you about is actually it's not really machine learning. It's graph algorithms that are awesome, nevertheless. And the theme here is to kind of overcome human biases that are present in the field with automated approaches. And this is the project that we are doing with the experimental group of Sebastian Will at Columbia University. And basically the aim is to detect laser cooling schemes. I will tell you in a second what laser cooling schemes are for ultra cold complex particles. And let's start with the first basics. So I told you if we build quantum simulator, we want to have amazing control over all elements. And the first thing that you do usually to get this amazing control is you cool it down super, super, super much, actually almost down to absolute zero. And this is, I would say, the first step that you do to obtain the quantum simulator. The problem, and to cool it down, you need to use a sequence of lasers with some properties, and the set of lasers and the way you're doing it is called laser cooling. So you need to have a laser cooling scheme to cool down your system absolutely, or close to absolutely. And how to do it, the scheme will depend on the atoms or molecules that you're cooling down, and in particular on their internal structure. And this is the messiest slide of this talk, but bear with me. So on the left, you have some energy levels of your atom or molecule. This is just to impress you that there are many energy levels in molecules or atoms. And problem is that the higher you are, the more excited you are. And if your molecule is in this excited state, it will spontaneously decay to something with lower energy because it likes it to be in lower energy. And taking into account this spontaneous decays, because this will be taking your molecules from one state to some other state, you want to detect there some valid scheme, a laser cooling scheme, that will allow you to pump your molecules from one state to some other state, and then your molecules will decay down hopefully to the same level from where you're excited. You want to have these cycling schemes that will allow you to keep your molecules or your atoms in your experiment, because the moment it decays to some state, other state from you where you don't pump it back, this is kind of lost. So you want to find this scheme that is where you cycle your molecules across energy level schemes. And people so far were looking for these schemes by hand, and because it's super difficult in such a jungle of states, they were using simplifying heuristics. And obviously the question begs to be asked if maybe we can make it better with automated approaches. And the, let's say, enabling insight is everyone we're looking at, all chemists and physicists, we are all looking at these energy levels as a ladder, because things are higher energetically. And and then the decay down is an arrow down. But actually all this can be represented as a huge graph with decay paths connecting different nodes, basically making connections between nodes, and each node is an energy level. So this huge graph is just the internal structure of a molecule, and laser cooling scheme actually can be represented as a subgraph that meets a set of conditions. So all this problem can be translated into find the subgraph in a large graph, and there are tools to that basically very, very efficiently. And what's really cool is I will just flash that because you may not care about what kind of things we put back into ultra-cold chemistry. But I think the main thing is for every molecule that we studied, so this is like dimer of carbon, CN, the carbon, nitrogen, for every molecule we studied, we recovered what was known, but we also found new schemes. And maybe interestingly, like just the scaling. So basically those are tabulated in some databases energy levels. So for small molecule, it may be like 50K states, but 6 million decay channels, because there are much more decay channels than every node, than the number of nodes. And it took 10 milliseconds for a graph to find the answers. But then the larger ones are like it scales pretty well for the problem at hand. And I think maybe to also, because I think this is kind of trivial application and like it makes total sense, but our co-authors before working with me, they did it for this carbon dimer carbon by hand, and it took the PhD student half a year to find the schemes. And not only we did it in 10 milliseconds, but also we found new ones. So was very happy, but also kind of crying. So I think he's happy. So, but it was a lot.
Can you tell us, like, from a graph perspective, what is a cooling?
Sure. what's a cooling scheme from a graph perspective. So the algorithm will be the following. First, find me such nodes that have energy lower than, because every node energy lower than something.
Okay.
All
of the nodes are linked.
So they have properties like the nodes. Let's say the most important for nodes is the energy. The most important for the decay channel for the edge is the frequency. And how likely it's go that way. So two properties of both objects, and then first you identify the starting nodes for your scheme, which have to be lower than some energy because you want to have access to them because some. Okay, forget. So they have to meet some condition on the property. Then you find all the nodes that are connected with this node with an edge, but with a condition that is this edge has a frequency of within certain range, because it's coming from constraints from the experiment. But basically you found all your nodes, starting nodes, then you find all the possible connections that you can excite it to. And then from there you find all the nodes from where this node can go. So all the nodes that there are edges in between. And so basically you find all possible kind of triangular paths. And then there is a formula depending on properties of this nodes and edges. And if this formula gives you a number that's lower than something, then you accept this as a potential scheme. If it's too much, if the number is too high, it means it's not valuable experimentally. So basically you look for many subgraphs, you calculate a very simple formula for each of them, and you either accept or discard. And then you give back the list of. And we're doing it in Neo4j because basically you need to start with loading your full graph. So it'd be hard to do with Python.
And how many nodes?
So depending on the molecule, either 50,000 or 3.5 billion nodes. So, and there will be more with polyatomic.
Like you said, you start with.
So and again, it depends, because if there are many
parameter, something that is intrinsic.
Intrinsic. If there are many states that have accessible energy, let's say, and it depends on the molecule, then you have many starting points. But this will be.
But you start at all points at once, or
yes.
all? Yeah. Okay.
All at once.
So this cycling solution may involve more than 3 nodes, because you said
yes.
triangles.
Yeah, I don't know how to.
Yeah, I mean, but the solution can span over a different set of.
It will have always this one, let's say, middle node.
Okay.
What means a star, and yeah, triangle was a wrong thing. So it's a star node with all the decay channels. And then if I give it to the experimentalists, they know they will need this lasers excited back to this node, and then it will decay back on itself to these nodes, then laser back and pumping star. And I think coolest thing in this project was that the schemes we found, whatever this means, get that, but they didn't follow heuristics. So basically it means that we were searching through the states of possibilities, for the space of possibilities, and we were handicapped because we were using wrong ideas. So that's very cool. And basically, this is my largest hope for automated approaches in science. So we can overcome human biases sometimes. And we gave access to new ultra-cold molecules, which will be of use for experimentalists. Okay. I'm super happy there was lots of questions, so I really don't mind. But I think I will just do a very brief, basically I will tell you what happened here, but without details. So just so you know, I told you that detecting phases of matter from measurements, for example, this will be a measurement of a bigger system. This is all spin systems. So every dot is just, it's a spin that can be either up or down. And for example, the orange means that it's down and the blue dot means it's up. So, and there is some external parameters you can play with usually. And this is very famous to the Ising model, where you increase the temperature from a very ordered setup where everything is pointing up. Get this order. So this was showing you as an example of phases. So what we can do with machine learning now is we can take the network and it will tell us, oh, there are two phases. All states are from here are one phase, and all states from here are a second phase. Awesome. But what we are missing as a community and really want to know is what's the order parameter. So what's the reason these two phases are different? I mean, in here we can see with our own eyes, but usually it's not that simple. So this is my I would say holy grail right now for ML for phases of matter, which detect order parameters. Because once we have a working machinery, we can really cool things with topological order parameters, but that's a story for another time. And basically, I'll just tell you that when I started doing interpretable machine learning, I was using model agnostic tools that computer science community developed. But I mean, now I know that, I don't know, maybe I was unlucky. There are some tools that I really love and they're awesome, and many tools that are completely unreliable. And I'm now at the stage where I'm like, okay, to make the interpretability really work, it needs to be task specific. So this is how we designed the Tetris CNN to detect, different order parameters. To detect phases along with their order parameters. And the reason why it's interpretable is we're using kernels of different sizes and shapes. We constrained, let's say, the problem so we can really understand that if this is what's going on, this is some order parameter. If this is the kernel, it's some other order parameter. Now I'm skipping, but this is explanation why we can do this mapping. This is how exactly this Tetris looks like. But basically, as a result, and we put some symbolic regression also on top, when we do the training, this is the epoxy training on our measurements, we can track which kernels are being used by the model. In this part, there's just kernel 1 by 1 being used, the rest are just dead. And by knowing that this is the correlator that is dominant in the data, we can use on top of that, on top of our network symbolic regression, and give you exactly the formula that the network is learning. So this is exactly what the network is calculating to make a decision whether the data point is in one phase or in another phase. And this is the order parameter we did expect in this setup, which is magnetization. So this is very, this is a toy model of toy models in phases of matter. So that's not very impressive from the physics side. But yes, and if it's more complicated problem, it tries different kernels and then maybe it goes to 2 by 1 kernel that is being dominant. And now we're doing more interesting setups than simulated Isings, which is true experimental data with noise and all that. And it's working very nicely. It told us the order parameters that we expected here and the ones we didn't expect in XY model. So this is we are writing it right now. But the true cool stuff will start happening when we go to the data that we don't know all the phases of. And this is the next step. And from the perspective of the model, it's not a big of a deal because here we had a square lattice. I showed you this nicely ordered measurements in Ising case, but then we go to different kind of lattices that are kind of shifted or they are triangular, and there are different phases that we know that there's something strange going on and we don't know the order parameters. And then it would be super awesome if we can go to this topological order parameters. I have ideas how to do that, but maybe it's more for physics physics audience. Okay, so that's the idea, to discover both phases and order parameters, custom-made solutions. and the open problems to sum it up. So I would say my research right now is on like going into two directions. One is AI for quantum physics, and I showed you those two snippets. But I'm also looking into Hamiltonian learning, and there are lots of interesting challenges for experiments they want to tackle, plus exactly understanding this, how we can use these tools for really unknown order parameters. And then there is, let's say, this computer science side of it, because the moment I got into interpretation, lots of questions popped up. And we are studying properties of good neural network initialization. I'm very keen into Hessians, as you maybe noticed that there's a pattern. So that's ongoing. Oh yeah, and I think all this let's say lost landscape intuitions are very useful to understand what's going on with this neural quantum states. I told you that we know we struggle with optimizing them. We don't know what's going wrong. And in general, I think that improving reliability and interpretability to use ML in sciences is a must. The scientific data create new challenges, as I showed you, with topological phases, so we can understand ML and the fail-safes even more. There are lots of challenges that slow down breakthroughs of quantum simulators, and actually some of you are excited about quantum computers. These are the same challenges that are slowing down quantum computers. And I'm also a bit curious about using this interpretability tools for AI that works for chemistry and biology, and what they learn, and if they really maybe also overcame some human biases in these fields. So if you want to know more about ML in quantum sciences, I recommend this book completely without any hidden agenda.
More questions? Already asked.
No, we ask on the. No, I was saying to ask on the fly. But there's no.
That's great.
Yeah, one thing I was thinking that so if you can rely on data which is prepared to exactly solve the problems, right? Because these are, if I understood correctly, these are the problems where you were working on for these interpretability. So problems for which exact solution is available, right? Which is a finite set.
Right now, I am in this regime, yes.
Yeah.
But the moment now we go to these different lattices. Okay.
Indeed. So the question is this: so if you can't rely because of the ability, and also they are like connected to approaches to the approximation
Yes.
of those. So how can you exploit the data in cases for which you don't have exact?
Yeah. So that's awesome. Thank you. And I think this is a really cool thing, because if your ML is an interpretable, and it will tell you, okay, I looked at this correlator when making classification into these different phases, you cannot really argue with that, because there is a correlator, you can compute it separately and see that this is what differs this set of data. But so this let's say is independent of data quality. Now we need to make the following question. So the network detected some phases, and we know the order parameter. Does it really tell us that these are the phases of the Hamiltonian that we planned on, building experimentally? Because probably there are many errors, many uncertainties, and this is not necessarily. So we solved some problem. Is it a problem we wanted to solve? You know what I mean? So the uncertainty in the data, if your approach is interpretable, is not messing with your result, but with application of your result, or interpretation of your result. So if you wanted to know, okay, I'm building this Heisenberg model, whatever it is, on some triangular lattice, and I want to understand and solve this Heisenberg problem with these different interactions. And now I'm building my experimental setup. I'm analyzing the data with ML, and it tells me, okay, there are these phases with these order parameters. It's correct in this experiment that there are these phases and these order parameters, but whether this experiment described the thing you wanted to solve well, that's a different problem altogether. So, and then maybe a different ML can be actually, you know, trying to understand this this problem more. But I think that I was showing this roadblock in experiments, this like, transferability from known regime to unknown regime. This is exactly what I was like thinking at, which is, can you really, so there are situations where, for example, you have Hamiltonian with two terms, and when you have those two terms, you can exactly solve the problem. Then you add the third term, and this basically, like you stop being able to simulate this system. So can you train your model on these two terms and it will understand something about the third term, or it's completely out of the question? And how to, you know, basically how to bridge theory and experiment is a very, very big thing. And I don't have good, like, you know, ready solutions for how to do it with ML, but I think very interesting.
Yes, exciting.